José Guillermo Sánchez León. I am from Spain. I taught in Mathematica and Mathematics at Salamanca University, Spain. At the same time, I was working in the nuclear industry, and later I was scientific consultant. For a few years now, I have used Mathematica in real application in different fields. You can find some of them in my books, Mathematica Beyond Mathematics, the Wolfram language in the real world. One of these applications is called BioMock, devoted for modeling radioactive substance in the human body. Is mainly applied in occupational exposed workers to radioactive aerosols. It can be also used in nuclear medicine for modeling the isotope spread in the human body. Sometimes I expand it with new options. I will describe in my presentation one of the last one. In this specific case, I will describe workers in a nuclear fuel manufacturing plant are exposed to inhalation of a small amount of uranium oxide. These workers moving between different areas where the concentration varied randomly. These concentrations are measured by static air sample, SAS. However, the quantities incorporated by workers based on the measured concentration and the resident time in the different area have larger uncertainties. For this reason, workers periodically undergo uranium urine analysis. We have developed a method where joining the urine samples data and the measurement from the SAS, the quantity of uranium incorporated by workers at the corresponding doses are estimated. We have a paper where it's described in detail the method. The method can be applied in a easy way using BioModWeb. BioModWeb is a mathematical application developed using Web Mathematica. Here is the address. Here is that. Later I explain something about them. This application needs several mathematical packages to work. I will describe how these packages work. We will need to know the urine excretion as function of the time after the intake of 1 becquerel. It is usually known as the response function. It can be done using a compartment modeling. A compartment model is a mathematical framework used to describe the spread of entities, in this case, an isotope, in a system by dividing into the distinct compartments. And we have developed a specific package with this purpose. I will load the package. I will illustrate with a easy example. This is the iodine model. This is an easy iodine model. I will describe how is the model. This represents the tyrod, but it is not important. The more important is that this model, the isotope introduced in the system through the compartment 1. From compartment 1 go to compartment 2, and from compartment 2 to compartment 3, and here I represented the arrow flow. I will need also the the transfer coefficient. Finally, this model mathematically is represented by a system of differential equation. Unfortunately, the package solved the problem. The first step is to build the compartmental matrix. It can be used easily. This represents this is the flow from compartment 1 to compartment 2, and this is the right transfer coefficient, and so on. Also, we'll need the initial condition. In this case, we'll suppose a single intake 1 in compartment 1 in T equals 0. Finally, this is the initial condition. Now we have the solution. This is the function that represents the quantity of iodine in the different compartments as function of the time. We can represent graphically the evolution of the iodine in the different compartments. Now we are going to use in a bigger problem. In these cases, the behavior of the uranium in the human body. We will need a very big system. This model are describing in the ICRP, International Commission Radio Protection publication. We can find the model for the uranium. It had more than 100 compartments, including the human alimentary model, the human respiratory tract model. Here is represented. However, I included many compartments. We have included this model in a specific package. Now we load the package, and here are the solutions I explained. This is the urine excretion every day for 1 becquerel intake the day T equal 1. This is the expression. This means that T is the natural day. You only need to write the natural day, for instance, the day 3 after the intake, and you will have the fraction of the quantity intake that it eliminated by urine excretion. We will need also the response function when you intake continuously uranium, 1 becquerel every day. We will need later. And here represented the evolution of the urine excretion in both cases. Actually, we will need to modeling the real process. We will need a more complex model. In real situation, the worker intake every day 1 quantity V the day T, and so on. This means that after a big number of days, the total quantity intaken will be than you can see. Here is an example. I assume a single intake 10 and intake 100 from the day 0 to the day 10, and so on. The day 12, 9 becquerel, and so on. And now we can represent what will be the estimated excretion of uranium every day. For instance, this day, the day 37, the worker eliminate by urine excretion 0.0678 becquerel. We are going to apply in a real case. The first step that we'll need is the information for a specific worker. We have the information with the resident time of the worker in every point, every day, and the concentration in this point. Of course, it is an estimated quantity and it has very big uncertainty. We load the data that we have in this case, we have in a Excel file. Oh, sorry, I need to previously need to load the data. No. Finally, the data has been imported. You can see the information included in the file. It means that the day one, he received an intake of this quantity. The same day received also this other quantity, and now we accumulated the intake for every day. We will need this information later. Previously, we must decide what kind of bioassay is the more appropriate to evaluate the intake of this worker. We can usually in the nuclear industry usually is assume a reference worker. Of course, we don't have the information of each worker. We assume a reference worker. Using this reference worker and the information that we have of this case, we must study what kind of bioassay is the more appropriate. We can measure the urine excretion or the fecal excretion or the lung retention, and by simulation we found that the more appropriate bioassay is the urine excretion. Here is represented by simulation for a typical worker what is the urine excretion. This period are the holiday period, and we found that in this period it where the uncertainty of the estimation is lowest. And forever, we will take the urine sample after 2 or 3 days without exposure. Here are the measure of urine sample for a specific worker. This worker, the first measure for this worker was taken this day after the worker started the exposures. The reason is that actually we implement the method when the worker had many years working in his work. This is the measure, the urine excretion this day, actually measured, and the corresponding uncertainty of this measure, and so on. We will need other information. For instance, when the worker starts to be exposed, and also what of the period that we want to know the intake. We know the intake for this year. Also, we will need the uranium isotopic composition, because the aerosol that the worker intakes is of radioactive of the enrichment uranium, and we will need the average isotope composition. With this information, now we can estimate the intake of this work, the estimated intake of this work. Here is the information. This is the more important information. This means that during this year, the worker received a dose. A dose is a measure of the isotope effect. It is 0.227 millisievert for this year. Now here we have represented the fit between the measure of the urine excretion and the fixed cure. We can see that it's a very good, it's a good fit. This process for real application will be complex. For this reason, we have developed a specific application as web application. The package has been integrated in a web application. It runs entirely within your web browser. It can be used easily without extensive knowledge of mathematics or Mathematica. This is the address. You can test. And this is the same problem solved in this application. Only you need don't load the data. Here is automatically visualize the data. You realize that they represent the value intaken every day by the worker. You realize that this is a random intake. Here represented the 3 highest values, and here are represented the moving average for the last 50 values. Here introduce the isotope composition, also the urine sample data, and other information, like the period that we need. And now you only need to evaluate. Now it has the information. You can find that here is the solution. At the same time, you have represent the victim. This is all. This is all. Only to finalize, you can find many examples of the real world in my book with the help of Rubén García Berasategui. This book including easy example of and real example of modeling, astronomy, finance, life design, chemistry, geography, machine learning, nuclear physics, and more. Here you can find additional information. Thank you for your attention.